So welcome to this session. My name is Clement Escoffier. I'm working for Red Hat as a Vert.x core developer. But this session is not really about Vert.x. This session is about Reactive. When I started to work on Vert.x 2 years ago, before I was doing something very, very different, I was an academics. I was working on dynamic and modular system. And while modular systems start to be trendy again, thanks to Jigsaw, I was at the end of my studies about that, so I decided to switch, and when I had this opportunity, I said, hey, yeah, look, Reactive looks cool, right? But at that time, I had almost no idea what Reactive was meaning. And when I looked on Google, I saw a lot of reactive stuff. So we had Reactive Manifesto, Reactive System, Reactive Streams, Reactive Spring, that's new, but Reactive Programming, Reactive Extensions, all those reactive words. And I had no idea what it actually means, because if you take all of them separately, they are completely different. And they were often associated with weird concepts like asynchrony, asynchronous, message, load balancing, back pressure, Excel, and spreadsheets. Whoa, the first time I saw that Excel was reactive, I was like, what? Come on, I'm not really reactive when I have to do Excel stuff, but yeah. So, and I did something that only academics still do today. I actually opened a dictionary. So today, because we are in 2017, I looked at my dictionary online. So this page really exists. It's from the Oxford Dictionary. And I looked for reactive. And he said two things. He said, well, reactive means showing a response to a stimulus. OK, fine. That's vague. But OK, I can do something with that. There is a second definition, which is actually very interesting. Acting in response to a situation rather than creating or controlling it. This one is actually very interesting and has a big impact on software. But those definitions were really not about software. And we had this physics definition, but I don't like physics. I did physics during my studies, and if I'm here, it's because I didn't really succeed to physics. So I decided to hack the page and to say, hey, come on, it should be software here. So I wrote this definition saying, a reactive software is a software reacting to stimuli such as message, request, metrics, availabilities, and stuff like that. That sounds right? Based on the two other definition, just mix all of them and so something that reacts. It's not new, because everything is reacting since the early days of computing. Like if I write something on my keyboards, there is some software that will handle those keystrokes. Or even your mobile phone that will react according to the level of battery or level of signals or Wi-Fi and stuff like that. So it's not new. There is something else that is interesting in this definition, is this part here. Acting in response to a situation rather than creating or controlling it. When we build software today, we generally know what we are doing, almost, sometimes. Yeah, OK, 50% of the times we know basically what we are doing. But here, it's really say you are going to write software that you don't control. You don't control what's the import of them. So when you write traditional software, you write the first line, and then you say that it will be the second line, and so on. So it's very linear. But in the case of a reactive software, it's not the case anymore. What will decide what the next line that will be executed is the events, those message, request, metrics, or availability, and so on. So all the stimuli will decide what is the next line. So can we say, is that the end of the flow of control where you were in control of your software? Or it's just a comeback of asynchrony, or the revenge of asynchrony? Because since the 80s, we try to avoid asynchrony as much as we can because we think that it's complicated. In this talk, in addition to understand what reactive actually means, we are going to see that asynchrony is not that bad. We made a lot of progress in the 80s to 2017, and asynchrony is something that we can tame very well. So reactive is big. We saw all those words. Let's try to position those words on a spectrum. This spectrum will have three stuff. On one side, we have reactive systems. That's an architectural style. We are speaking about architectures for distributed systems. It's actually, we are going to see that, but it's actually based on the idea that distributed systems need to use message and asynchrony to work. So here we have things like manifestos that define reactive systems, actor, messages, resilience, elasticity, scalability, asynchronous, are all related to this reactive here. On the other side of the spectrum, we have programming. while reactive systems is really on the architectural level, reactive programming is about programming, it's about code. It's a set of library that will provide you a development model to tame the asynchronous beast. So here we see words like data flow, event, observable, or even spreadsheets. Don't worry, I'm going back to this. In the middle, we have another one. It's the middle, but it goes a bit further to the reactive programming part. It's called reactive streams. So reactive streams is just a set of API for classes. You can read them because they are very, very simple, that provide a protocol to build back pressure between a publisher, so a source of data, and consumer. We're going to see that too. And here, the terms that are often associated with this reactive is data flow, again, back pressure, and non-blocking. If you look at the Java technologies, we are in Java conferences. So for reactive system, we will find Akka, which is a pure actor model, and Vert.x. For the reactive stream system, we see a lot of implementation of reactive streams today, like Akka streams, RX version 2, or Java version 2, Reactor from Pivotal, or Vert.x. And on the reactive programming side, we have Reactor, so Spring Reactive, Reactive Spring, Reactive Extension, and Vert.x. Oh, we have Vert.x in the 3 categories there, and there. At the end of this presentation, I will show you a demo of how Vert.x can be used to build a reactive application that will be the 3 of them in one, and why it makes sense to build that. But before going to that, let's have a look to this application. I started software more like I was not good enough in anything else, so I decided to do computer stuff. Mostly because I wanted to do video games, but yeah, I failed. So I was doing something very boring, like management API or management software. Like I had users that has this beautiful black and green terminals. I was adding stuff, saving. It goes to a database, and then was getting the list of all the records that has been saved. Something very, very simple. And at that time, so it was a bit more than 15 years ago, everything was fine. I was able to build my application, it was working. And then my application started to be a bit more complicated, and the company decided to take some code and to extract it to another service. Say, yeah, but you know, this code, you need special business understanding, so you cannot build it there, so we will extract that. So for example, the pricing system. It can also be non-functional, like your user management will be externalized. If you do microservices, it's what you are going to do today. You have a monolith, and you try to extract a couple of services from your code base, and they will have their own life. So we have some services, and my application is going to call them. Obviously, we have the opposite direction. So while before I was only providing a black and green API, now some other software from my company, but from other company, also wanted to rely on my pretty cool features that was just saving in a database. But yeah, so I had to provide an API for that. It was a long time before REST, so at that time it was more Callbacks stuff. But yeah, I did it. So I had my API, and everything was working, and so on. I have to say that after that I left. But another thing that happened to this application is that they start ingesting a lot of data from sensors, from whatever things you think, so mobile and stuff like that. So a lot of data was coming inside the application. Okay. Users. Time fly. Users doesn't fly yet, but they start to be very, very picky. They don't want to refresh page anymore. They don't want my cool terminal kind of UI. They really want something on their mobile phones, and they don't want to pull the information. They want the information to be pushed to the phone, to your web page, and so on. So, for example, you go to Facebook Messenger. You don't want to refresh the page every time that someone has written a message to check if someone has written a message. The message gets printed for you. So exactly this. They all want that. It's not easy to build. And obviously, as this whole application started to be a very, very big mess, because it was not designed to be that, we decided to put some auditing system or monitoring system and stuff, so it makes things even more complicated. So, okay, fine. Let's build this. Well, Can be complicated, right? Because all those interactions are distributed. And all the softwares we are building today is a distributed software. And what we know about distributed software? Distributed systems fail. That's their definition. You can be as good as you want, use the technology as you want, it's going to fail. You don't control anything in that case. You don't control the users. You will never control the users. If they decide that your website is really cool and it refreshed or all the users go to your application at the same time, so you have to handle the load. The software, same thing. You don't control when they are going to call you. And the amount of data you are going to ingest in your application, neither. What is interesting is that this part here, this part is generally what we see in a distributed system. It's nice to take some part of my code base and to extract in its own process and stuff like that, except that it may fail. It may be under update. It may be slow. So you need to handle that. So you need to check when a service is not available, what you do, and when you are dealing with a database, you need to be sure that it's answered in time. And databases are not the fastest system we built. So yeah, we need to do that. And when you build such kind of system, what happens is this. My monitoring system that was like that, generally pretty quickly, it becomes like that. It's dead. It's exploding. It's blown up completely because it's just very complicated. And distributed systems are complicated. So to handle this, let's start to see the first reactive terms we have seen, which is reactive systems. And reactive systems is an architectural style to build responsive distributed system. It has a very simple idea. It's just say, yeah, all my components are going to discuss using asynchronous message passing. Because of this, I'm going to be elastic and resilient. And by mixing all three, I'm going to be responsive. If you're interested by the reactive system, it has been defined by the Reactive Manifesto that is available here. It's only 4 pages. You can read it very, very quickly. So, but how does that work? The whole idea is this asynchronous message passing. My components are going to send message to each other. And when you send a message, you send to a virtual address. I'm not sending a message to one guy. I'm sending a message to a virtual address. And, well, I don't know to which one it's going to be dispatched. I'm not in control of that. So here I have represented a message backbone, but it's not necessarily the case. On the other side, I have a consumer that will subscribe to an address, and the system will dispatch the messages. So what happens if I have a lot of messages? Well, it's very simple. If I have a lot of messages, I can just spawn new consumers that will listen to the same address, and the load will be dispatched among this set of consumers. And if one day one consumer crashed, like the first one here, it's not a big deal because as I am using asynchronous message passing, my application is not blocked. It can still handle the other request and send the other message to the remaining consumers. And when the dead one is respawned, then it will be part of the pool and will get message too. But what about this failure management? Then it's a bit up to you and up to the system, because the message will probably come back and say, yeah, well, okay, the message is dead, and you has not been processed, so you need to handle it. Maybe you can retry. Be careful, retry, distributed system, idempotence, can be tricky. Or just forward the error to the user, say, yes, sorry, you have to restart or retry your action. It's not part of the reactive system definition, it's just really up to you. So actually, my distributed system should be so easy. The only thing I should do is just putting message everywhere. Should be fine. The only issue is that if you do this with a traditional development model, meaning that you have threads that will handle the requests and will keep the request the whole life, what will be going on is that you will need a lot of threads to handle the load, and you will get this, a kraken. Too many threads. Threads are heavy. Threads, generally, you should not scale too much number of threads, because with each thread, you have a cost in terms of memory, in terms of CPU, because you will switch between threads and so on. So you should avoid creating too many threads. So how does that work? You need to embrace asynchronous. So for this, you need to write code in an asynchronous manner. Let's see that. In the ideal world, if I have 3 requests, I will have my threads here, and it will do task A, task B, and then task C. Everything is fine. My CPU is busy. It will do task A, B, C. OK. In the real world, it's a bit more tricky because all those tasks generally do I/O stuff, and I/O is blocking. So A will, for example, start calling my pricer service, and during that time, the thread is blocked. Then we come back, continues, and it needs to call the database. Blocked, waiting. Same thing for the other task. So you see the difference here? Just a waiting time. Do you like waiting? I don't like waiting. It's a waste of resources, waste of my time. So the asynchronous idea is to say, yeah, well, while something is blocked and cannot make progress, not a big deal. We will just use and execute something else. That's fine. Only issue is that to do this, so it's what we see here. To do this, we need to, instead of writing those tasks in one big monolith, we need to split them in, well, in a set of subtasks. Like this part here, then it's calling my database or my pricer service, and when it comes back, it will do that, and then the database, and when it comes back, it will do that, and so on. So we need a development model for this. We also need to rely on non-blocking I/O. And we must not use thread for this, but more task-based concurrency, because this will be my single threads. So if you want to write asynchronous code, the first thing you will do is say, OK, what about callbacks? Actually, callbacks is really interesting because it's Hollywood. In a synchronous world, you will write a method like that, compute A, B, and return the result. On the consumer side, you have the resources, the result, and you wait for it. You don't know what compute is doing. On the asynchronous way to do that with callbacks, you will pass a callback here, this part, and when the result is computed, then it will just call the callback. On the consumer side, it's really Hollywood in the sense that don't wait. We are going to call you when the result is available. So we just pass a callback like that using Lambda, for example, and that's all. Look at this structure here, async result. Because actually here we are a bit lying to you. There is two outputs to this. The first one is that we have a result. The second one is that we have an exception. Hey, yeah. Async result, as we cannot throw exception in an asynchronous world, so async result will capture either if it was successful or if it was a failure, and then you have the exception. So if you do that, if you use callback to, for example, to build an HTTP server using Vert.x is going to be like that. We have a request handler here, and every time we have a request, we are going to call this method. OK, so that's my callback. It will be always using the same thread, fine. And then we have the listen operation that can take time. There is a lot of things happening at the operating system level to start an HTTP server. And when it's done, you have this asynchronous result here. Looks good, right? Let's see another example. I want to deal with my JDBC database. So I need a connection for my connection pool. This is asynchronous. Once I have my connection for my connection pool, I have my yellow stuff, my yellow code. And then I do my queries, select star from products. OK, this is asynchronous too, so I'm going to my green callbacks. Then I have my stuff and so on, so I'm iterating over the lines and so on. And then I need to release the connection, so I need to call close, which is also asynchronous. And that's my blue callbacks. We have 3 nested callbacks. So if you pick this development model, the first thing you will do is take your IDE and resolve the space versus tab issue. Because what you will do is to set your annotation to 2 spaces. No tabs, 2 spaces. Because it's just too narrow, so you need to reduce it. All Vert.x core and Vert.x ecosystem is developed like that. Believe me, it's not necessarily readable every single day. Whiskey helps to read this. To avoid that, we can use reactive programming. Reactive programming is actually very simple. Do we have people using Excel here? Or Google spreadsheet or stuff like that? No? Oh, yeah, we have a few. So those guys are the true reactive developer. Yeah, we are going to explain that. I do a lot of conferences, and the most awful experience when you do conferences is not the food in planes. No, or the jet lag or stuff like that. It's my expense report. I'm working on Red Hat. Ask for a Redhatter how looks our expense report. It's really helpful. But the fun part is that it's kind of reactive. Because I fill my line, so for example, lunch, 15 euros. Spain is cheap. Coffee, 25 euros. I need a lot of coffee. Drinks, 45 euro. I drink a lot of whiskey to understand my code that I just wrote. And so I have my total. But actually, what I do is that I've wrote this cell in relation, so depending on the other cells. So there is this cell that observes the other cells, and as soon as there is a new value in these other cells, it will update the total. Right, we all did that. Let's take a time machine. Because at the beginning of my expense report, I just wrote food, my lunch, so it's 15. And over time, then I wrote 25 in coffee, so I have 40. And then I write my drinks amount, and then I have 85. So my cell is not one value, it's just a sequence of value over time. That's what we call a stream of data. And reactive programming is about stream of data. It's stream of data that we will have, and we will observe and apply functions to every single value we have on this stream of data. So for example, imagine that I have this red stream of data, which are all the integers, 1, 2, 3, and so on. Then I can observe this stream and say, for every value from this stream, just add +1. And we have the green stream. Okay? And then we have the blue stream, which is a bit more complicated that you can't actually do in Excel, is to take the last two values from another stream and do a sum. It's probably like that they compute my tax in France, but something very complicated. If I want to write this in Java, I will probably use Eric's Java. So this code is for Eric's Java 1, but concepts are the same in Eric's Java 2 or in Reactor. So I have a first observable, which are all my integers. Then I observe it. See, I do ops1. .map, I'm applying a function to see all the values from this observable. I'm just doing +1. So I'm not returning one value. I'm actually returning a stream of all the values +1. Right? Then I have my blue observable, which observes the ops2 and takes the last two values and computes the sum. Here, it's map because I'm returning a single value. Here it's flat map because I'm returning an observable, which is just my sum. It's actually an observable of a single value, but that's the API. So it just returns this observable, and then for my stream, it will just flatten it. When you do RX or reactive programming, don't forget this part. Believe me, I forget it every single day. And if you don't, it doesn't do anything, because I believe that reactive programming is actually a bit French, so very lazy. If it doesn't have to do anything, it won't do anything. If you don't subscribe, nothing happens. If you subscribe, OK, I will do the work, and things will start executing. So what's the relationship between this and asynchronous? It's because we can use those observable IDs to map asynchronous stuff. Like observables, then that's a stream of data. So for example, all my requests for my HTTP server, that's a stream of data. Every single request is inside my observable. I have interaction, for example, with my pricer service. So I'm sending a request and I wait for a result. I can use a single of this because my result is a data stream of one item. So it's what we call a single. And then we have completables, which is actually singles where you don't really have a result. You just know that it has been successful or not, like void. So fine. If I rewrote using those structures, my JDBC example, here it is. I get a connection. That's a single. Then I do a flat map on it. I execute my query. That returns me the sequence of rows, observable of rows. And then I return that, and then I map it. And for each row, I just create a product. That's all. So my 3 nested callbacks are just those 10 lines. Much more readable. So yes, you can say, yeah, it's not that simple and so on, but pretty quickly, you get it. Actually, I'm using almost always the same operators. So even if RX is providing lots of operators, I probably use 5 of them. This part is actually interesting because you can say, when I've finished to iterate over the whole set of rows, then I just close the connection. I just use the term iteration, but that's not true because things can happen at the same time. It's not an iteration like 1, 2, 3, 4. If you have 2 rows, then things will be called at the same time. So is everything working? Yeah, more or less. But imagine the case where my application is ingesting data, and there is way too much data for my application. So what is going on? My application is going to die. Why? Because when I'm ingesting my data while using reactive programming, I just have my observable of JSON, okay, and then I use concat map, which is a bit like flap map, but can be called only once at the same time. So it's like enqueuing all the job and doing one, then the next one, then the next one, and so on. Really sequential work. And if process takes too much time, what's going on? Well, I have an internal buffer here, and it will put the first element, second element, third element, but if the buffer is full and my concat map still didn't return, I have a buffer overflow. So you can try to tune the size of the buffer. Generally, it doesn't really work. It works only if you have a bit bump in your process, but if you really have too much data, it doesn't work. We need to find another way, and it's where back pressure comes into the place. The first thing you can say, well, I don't control my source, so if I don't control my source, I just have one thing, is to say, okay, I have to give up with some data. So data loss. So for example, when my buffer is full, all the new values are just dropped, or the oldest value is dropped, or so on. So you can do whatever you want. So in RX1, you will do it like that, on back pressure drop, and you have a couple of strategies and so on. So it's fine. But is data loss acceptable? Generally, it's not, right? I'm not sure that I want my transactions lost, or especially payment or stuff like that. In that case, you need to have a full back pressure. But back pressure only works to the condition that you have control on the source of event, which is generally not the case when the source of events is called users or sensors from the IoT world. In that case, you don't control them. We tried for years to control users, but it doesn't work. Too bad. So in that case, flow control, if you control it, so you can apply a flow control strategy where the source the consumer tells to the source when it can receive data. So it reverses the control completely. Before it was the source that was sending data, and now it's the consumer that say to the source when the data need to be sent, based on its capacity. So there is different model. Reactive Streams is the most popular in the Java world today, and it's going to be embedded in Java 9 as under the name Flow. So it's the same API, 4 API, publisher, subscription, consumer, and processor, but they just move it to a new package named Flow. So all application based on Reactive Streams doesn't compile anymore. Good job. But well, just easy refactoring. There is other stuff like Vert.x that provide an easier model, which is just pause resume. So when your buffer is full, we pause the stream, and when it's back on track, it just resume it. Basically equivalent. You can prove that one is equivalent to the other one. In Reactive Streams, how it works, the consumer will get a subscription from a provider, or from a publisher, and then you can call request, and request X is the number of items that I ask my source to send me. So for example, it's my size of my buffer, and so on. And when my buffer is empty, I will ask him new data and stuff like that. Don't wait until your buffer is empty, but do be smart there. So that's Reactive Streams. That's simple. It's just about back pressure. OK, let's have a look at Vert.x now. So what is Vert.x? Vert.x is a toolkit to build reactive and distributed systems. Unlike a lot of reactive stuff, it has been designed and developed with reactive in mind since the first line of code, before it was hype. Actually, we can say that Vert.x was hipster before hipster were invented. That's cool, right? So we had this idea of things need to be reactive, react to events, to stimuli. And to do that, we provide asynchronous non-blocking development models. The plural is important here. We will see that. Simplified concurrency. We have an event loop. Because we are non-blocking and because we are using this asynchronous non-blocking system, it works very well and it scales very well. And why we have models and not model is because we are polyglot. By default, it will be Java. But we provide the binding to the API in, I need to read, Scala, Kotlin, Groovy, Ruby, Ceylon, and so on. Go on the website, you will have the whole list of language. When we say we support it, it's not like we use interop. No. We actually generate our API with a construct of every language. So for example, if you're in Scala, you may not use Rx. You probably will use futures, because futures in Scala are really well integrated, and so on. Vert.x also have a cluster event bus. We are going to see that. And Vert.x is used today in many, many use cases. And those lists here is just production use we are aware of. Why Vert.x and Reactive? Because it has been designed with Reactive in mind. But actually, we also support the whole spectrum because we had this idea. So our goal is to build reactive systems, so better distributed systems. And for this, we support reactive streams for back pressure and also a couple of other models. And we provide reactive programming in the language or in the model you want. In my presentation I will do here, I will use RX1 because it's what we used as an explanation. So let's take this application. And if you want to have the code, it's just there on my GitHub account. And I won't show this part because I'm running out of time. So we will build the rest. So the first thing is that my database is going to provide an RX API. So every time that I insert something, I will get a signal telling me that it has been successful or not, and I get the items that has been inserted with the ID and generated ID stuff. So how I do that? Well, I get my body a string, for example, and I just insert it in my database. And when it's done, because this is non-blocking, I just write my response, and that's all. For a list, it's a bit more interesting. I get my database, and I will get my set of rows as an observable, okay? And every time, for every single data, every single row, I'm going to write my row, or the result of my row, so my product, directly in the HTTP response. I'm not building the word responses in my memory. Because if I have a lot of rows, I probably will get an out of memory exception. I don't want that. As soon as I have a row available for my database, I want to write it immediately to my HTTP response. I don't care if the browser gets an out of memory. Anyway, it's Chrome, so it's probably already have many out of memory because I have too many tabs. So then, as soon as I have something ready, I just push it to the browser. To do that, I'm just using chunk request. Chunk request is not something new. It's not something from HTTP 2 and so on. This is HTTP 1.1. It's very old and underutilized, and it's very, very powerful. You can send the response, your HTTP response, chunk by chunk. That's why they call it chunked, actually. OK, well, interacting with my pricer service. Then I can just retrieve, and for every row, I will call my pricer service using a web client, which is a Vert.x HTTP client, like that. OK, fine. What is important here is that this call will happen several times at the same time. Oops, sorry. If I have 2 rows that are available, I will call the pricer immediately twice. The pricer, I don't care. The pricer has to scale. It's not my business anymore. That's the pricer stuff. And every time that the pricer responds, then I'm here and I write my response. That's all. Yeah, but here I'm using an URL. So I know that my pricer is there, and it's not really reactive system stuff where we have to use a virtual address. So for this, Vert.x comes with an event bus where all my components can interact using messages. I send my message to an address, which is pricer, for example. I don't care how many instances of pricer I have. I will just send the message and wait in a non-blocking manner my responses. Very simple. Next things. I want to push the data as soon as someone inserted the data directly to my browser using a WebSocket stuff. Yeah, the issue with WebSocket is that it doesn't work on all browsers. Yeah, there are still people using Internet Explorer 6. That's the world, and we have to deal with that. So in Vert.x, we have something called SOC.js bridge that brings the event bus directly inside your browser and will negotiate the communication using WebSockets if possible, and will degrade to long polling if it's really Internet Explorer 6. And in that case, once you have the bridge, sending something to all the browsers that are using my application right now is a single line of code. This one here. Vert.x.event-bus publish some addresses, and my JSON and my browser get the event bus, will subscribe to the product's address, and will just retrieve the result, get the JSON. we skip that. I want to show you some demo. So, let's go. How long do I still have?
7 minutes.
Okay, so I will just run the last one.
9 minutes.
So actually, all the code I've shown you is this class here. All the code, it's 80 lines, and believe me, the font is big, so you can read it. So that's all. And oh, yeah, come on, I can save some line here. 79, 78, yeah. So it's actually very simple. I have a main because Vert.x is a library, it's not a framework, so I just can write my own main. I just create my cluster Vert.x, which means a clustered event bus, and I just deployed a set of vertical. Okay. And then to build my REST API, I use something called router, where I just declare routes like /products and so on and so on. And this is my Suck.js bridge, and it's because I will have a very beautiful UI, believe me. I'm not a web developer, so bear with me. And then I initialize my database with a set of products, and when it's ready, I just do stuff, and that's all. And that's the code we have seen. Get products, and add products with my, yeah, here is my event bus stuff. So if now I, going there and trying to show you my cool interface, here it is. So how it works, to display this, you saw it open a bit later. It's because it does an Ajax call, and it gets the result as a chunked responses. So no matter, well, if we really will have very good eye, we will see that it displays them one by one. Then I can just add a product, say, let's say beer. I will need beer after this. Here. So as soon as we have this, it calls a pricer and so on. So if I go to the same page, up from here, so for example, in Safari, and I say, in addition to beer, I need whiskey. Oh, I just want to do that. Boom, you saw it? To arrive at the same time. Why? Because I have my Suck.js bridge. And what happened behind the scenes is that I'm inserting this new data to my database, and I'm publishing the new data to my event bus. And because my browser is connected to my browser is connecting to my event bus, it just gets it. That's all. Very simple, 100 lines of code. I want to show you one last thing. I have a Google Summer of Code student. If you never apply to this and you are a student, do it. If you are a company or interested in contributing to open source project, apply to, because it's a really good experience to have such students. And he worked 1 week. Well, no, it was 3 weeks ago, but I have the version from 3 weeks ago. And he built some very simple monitoring system using Vert.x. He built this. Less than 1 week of work, and he's undergraduate. Yeah, asynchronous is hard, right? If an undergraduate student can build that in less than a week. And he's not a UI guy, so the UI is just some CSS stuff and so on. And it actually gets live data. So if I do some other stuff like tequila, I love tequila too, then you see that the number of event bus, so we saw the one here, the number of delivered message and so on, the number of deployed vertical and so on, that's all running. And he builds that in less than a week. So imagine what you can do as a professional. You have no limits anymore. So let's go back to my slides and to conclude. So what about reactive? Reactive is just about asynchronous, and the revenge of asynchronous. Since the 80s, we try to avoid asynchronous because we say that it's complicated. We reach a point where it's not as complicated as it was before, and actually, it will make our application better because the world is asynchronous. All distributed systems are asynchronous. So instead of hiding it behind synchronous blocking API, just embrace it. Reactive systems, on one side, guide you to build better distributed system based on responsiveness. Then, because You have streams and stream of data. You need to handle bike pressure. You have reactive streams. That is a protocol that lets you manage bike pressure, local bike pressure. And then, because code can be complicated, we have reactive programming where that gave you a very nice API to tame the asynchronous beast. So you say, should I use reactive streams directly? No. Because now what we see is that all new reactive programming libraries, such as Reactor or Eric Java 2, are based on reactive streams, and you don't have to think about reactive streams anymore. You're all set. You just have a nice API to develop a asynchronous application with, in mind, what you want to build is a reactive system, because better distributed system will be good for the world. If you wonder about Vert.x, Vert.x has a very different way of thinking about your system if you compare it to more traditional framework. With Vert.x, you are back in charge. You can shape your system as you want. You want Kafka, we have Kafka. You want MQTT, we have MQTT. You want Camel, because Camel is great if you integrate legacy system, because don't write a reactive system in a big bang. We have Apache Camel integration. You shape your system as you want. You are responsible of what you do. You can use the main method I used. We have also a vertical deployment and stuff like that. Just up to you. You decide how you want your system to behave, and you are back in charge because there is no magic. You develop the system as you think it should behave, not as the framework think it should behave. Thank you very much. If you are more interested about this, we released a book a couple of weeks ago. Should be months now, maybe 1 month ago. Where it is? It's there. Building reactive microservices in Java. It's all about Vert.x. You can get a version for free to this URL here. And does that work? No. OK. So let me. If you want the slides, yay. If you want those slides, they're here. Thank you very much. And if you have questions, do I have 1 minute, 2 minutes for question?
5 minutes.
5 minutes for question. But I don't see you, so if you have questions, just
Raise your hand.
Well, no, don't raise your hand. I don't see it.
Yeah, we have one person with the
We have someone that is not as I am, so can see you. Any questions? So see, I don't see you, so.
Can you elaborate a little bit more on Event Bus? Like, what is it? How it lives in like?
That's very confusing. Where are you?
Yeah, here.
Oh, okay. Thank you.
Yeah. So, can you elaborate a little bit more on Event Bus? Like, how it? What is it actually in Vert.x world? Can I, for example, I don't know, substitute it with Kafka or like whatever, or is it something embedded? Does it live on vertices, or where does it live? Like, actually.
So how it works? The Event Bus is built in Vert.x, and by default, it will just use a cluster manager to discover all your nodes. In my demo, I use Hazelcast. We also have cluster manager for Zookeeper, Ignite, Apache Ignite, and Infinispan. And then the communication between the nodes is a pure TCP things. However, you can use Kafka, you can use Artemis, IMQP 1.0, or even RabbitMQ to do almost the same thing. Also, this way I can see you. So it's up to you. Again, Vert.x is about freedom. We provide you something. If you're not happy with what we provide you alternatives, and you can pick the one you like. By default, the Vert.x one doesn't require any server to run. It's kind of serverless, but doesn't mean serverless. So it works out of the box without anything. If you use Kafka or IMQP 1.0, you will need a broker or router or something like that. So just a question of trade-off. It's about freedom, so you pick the one you like. Do I have another question? If I stay here, I can see you. We have one here. Where is my? Don't fall.
That was sporty. When you publish a message to the event bus, is it possible to set like a maximum wait time for waiting for the response?
Of course, we have a timeout. We have timeout management for all interaction, all asynchronous interaction. That said, what about timeout? Timeout is a very broken way to think that something has failed. But you are in a distributed system, so you have A sending a message to B, and A get a timeout, because after 5 seconds, it just gave up. What does that mean? That means that maybe the message between A and B never reached B. It's fine. OK. Maybe B process crashed. It's fine. But maybe B was executed successfully, and the reply between B and A that went lost. In that case, you need to think, OK, if I'm in this case, can I really retry? Can I send my message back or not? Because it has been processed by B. So be very careful with timeout. It's the only way we have right now to think that something was a failure, but we are not sure that it was really a failure. Welcome to the distributed world. How cool is that, right? It's like Schrödinger cat everywhere. If I look, I'm sure it has failed. If I don't look, maybe it has been successful. Any other question? I don't see any raise. Thank you very much. If you want Vert.x stickers, go to the Red Hat booth. We have plenty of them. Thank you.